is the highest occupied energy level. In case of metal, we have seen that it is highest occupied energy level. In this semiconductor, what happens is it is average energy of the electrons, because electrons will be jumping from valence band to conduction band to valence band. This will be happening often. Okay, so that where this Fermi energy will be, it will be exactly at the half, at the middle. So to write in the equation form, that is E of F is equal to half of Eg. We can write like this. Okay, that is Fermi energy is equal to half of Eg, which we have. Fine. So today we are going to derive this. So yesterday I have given you the brief introduction of the semiconductor, and no questions will appear on the basic things. Only the advanced things which I'm going to teach you from today, they're going to ask in this only. So what is we are going to do? The relation between E of F and Eg. Okay, this we are going to find out, right? In intrinsic semiconductor, where in intrinsic semiconductor. Okay, in intrinsic semiconductor, what is the meaning of intrinsic semiconductor? Intrinsic semiconductor is nothing but it's a pure semiconductor. This is called as the pure semiconductor. In this pure semiconductor, what happens is number of electrons R is equal to number of holes. Number of electrons is equal to number of holes. Fine. Or we can say concentration of electrons is equal to concentration of holes. Right. So that is the property of intrinsic semiconductor. We have not doped it. If we dope, what happens? Either number of electrons will be more, or number of holes will be more. Okay, so this will be the case. One of the thing will be increasing. So if number of electrons are more, we call it as if number of electrons are more, we call it as N type. If number of holes are more, we call it as the P type. So there are two types of semiconductors in the impure semiconductor, that is extrinsic semiconductor. But what we are considering here, we are considering the intrinsic semiconductor. That means no dopant is added. Yeah, you are correct. So no dopant is added. That is the intrinsic semiconductor, pure semiconductor. In yesterday, I have given you equation. What is that equation I have given? For Ne and NH, I have given the equation. That equation, it goes like this. That is 4 root 2 divided by h cube, then pi me star, then this is kt, okay, to the power 3 divided by 2, e to the power E of f minus eg divided by kt. So this is equation for Ne. So we have to equate this equation. So this equation is equated. This equation is equated. So here I don't have space, so I'll write here. So this is equation for Ne. Equation for NH is what? That is again more or less same. That is a pi mh star it will be. What is mh? It's mass of hole, mass of an electron, into kt to the power 3 divided by 2, e to the power minus ef divided by kt. Okay, so these two equations I'm equating. This is equal to this. Okay, this is LHS, and this is LHS, and this is RHS. Let us equate these two equations. What happens when I equate these two equations? Okay, so this one get cancels. Pi will go kt, and this kt will get cancelled. Here there is me, here there is mh, so it remains. And okay, remaining all things will be like that, right? So in the examination, don't bother about this. You can skip this step and directly you can write Ne is equal to nh, that is equal to, okay. So what remains in this LHS? In the LHS, me star to the power 3 divided by 2 will remain. Then this term e to the power ef minus eg will remain, okay. That divided by kt, it is remaining, is equal to, in the RHS term what remains? This is the RHS term. In the RHS term it is m h star will remain to the power 3 divided by 2. Then this term will remain, e to the power minus ef divided by kt is remaining, okay. You can start from this step. You can skip this if you're able to remember this, well and good. Otherwise you have to write this one step, skip this step, you can write this step, okay. It will be more easy. Fine. So what we are going to find out from this equation, what I want from this equation, I want this ef. Okay, where is ef? Ef is over here, and also ef is over here. So there are two efs in this case. So we'll take to the left hand side this ef. How to take? Let me take this is equal to mh star. Then me I'll take this me, mass of an electron, effective mass of electron. I'll take this side. Okay, when I take that side, it will be me star to the power 3 by 2. Is it correct? Fine. Then I'll take this term, this side. So e to the power ef minus eg divided by kt, that divided by e to the power minus ef divided by kt. Okay. So this is what I get from this equation. Then this is, when I take this denominator to the numerator, what happens when I take denominator to the numerator? It will be e to the power e minus eg, it will be plus ef, this is ef divided by kt. Okay, when I take this to the numerator, it will become plus positive, is equal to mh star divided by me star 3 divided by 2. This is as it is. Okay, so this will be 2ef, 2ef to the power kt. Okay, let me write that this side, e to the power, it is 2ef minus eg divided by kt is the answer for this. Okay, now what I'll do is I'll take ln both sides, because I want this EFF, no. So taking ln on both sides, ln, that is the natural log, ln on both side, what happens when I take ln on both side? Okay, apply ln to this. When I apply ln to this, I remain with this 2ef minus eg divided by kt. Okay, is equal to, when I apply ln to this, it is ln of mh divided by me, a star is there of course, to the power 3 divided by 2. Okay, this you can write it as 3 divided by 2 will come here down. Okay, 3 divided by 2, then mh star. This is simple mathematics I'm doing, nothing else. Okay, so this much it is the ln is there, ln of this bracket term. This is the answer for that. And now I'll take this term in this right hand side. Okay, I'll take eg again to the right hand side. Everything we should take to the right hand side and keep this only EFF, that is Fermi energy, in the left hand side. Let us do that. So this is 2EF. Okay, 2EF is equal to, this is 3 by 2 ln of mh star divided by me star. Okay, then minus, this is there, eg minus eg is there, I'll take to the right hand side, it will be plus eg. Okay, So first we should take this kt, we should take, so kt will be here. When I take kt first, kt will be multiplied with this, okay, kt into 3 by 2. Then we should take this minus term to this side, that will be positive. Okay, then eff, this is eff is equal to, right? So this 2 I'll take, 2 means it is 3 by 4 kt ln of mh star divided by me star, okay, plus this eg divided by 2. eg divided by 2. This is the last step which we are getting for Fermi energy. Okay, Fermi energy is equal to this equation we got, right? But what happens is practically, okay, practically me star is equal to mh star. Okay, me star is equal to mh star. When I substitute me star is equal to mh star in this equation, what happens? What happens? Ln of 1, it becomes 1, right? This becomes 1 when I substitute both the equation. Ln of 1 is what? Ln of 1 is 0. Ln of 1 is 0. So this whole term will become 0. What I remain with then? I remain with EF is equal to EG divided by 2. So this is what I wanted at the end. Okay. So it's very simple mathematics we have seen now. Here Me is equal to Mh practically. Okay. Mass of an electron is equal to mass of the hole we have substituted. So what happens? This ln will become 1. Ln 1 answer is 0. So this whole term will be 0. I'll get EFF is equal to EG. Okay, by graphically we saw, by theoretically we saw that this is coming exactly in the middle. And now what we proved is, we proved that this EFF, that highest energy occupied level, will be exactly middle of this forbidden band. This is a forbidden band. Okay, that is energy band gap, that is exactly at the middle. Quickly let me go through this, what all things we have seen. We are basically finding this relation between these two terms. One is Fermi energy and there is energy band gap. Okay, in the intrinsic semiconductor what happens is Ne is equal to Nh. Any number of electrons or concentration of electron, number of holes or concentration of holes. In the intrinsic semiconductor both will be same. Okay, because it is pure. We know the equation for this, we know the equation for this. Substitute equation of that, substitute equation of that. Okay, and what all things are common, those will get cancelled. So in the left hand side I remain with this equation, in the right hand side I remain with this equation. In the examination you can skip this step and you can write starting from this. Okay, but with the description, what is the description? This is, these are what bands, where it is coming, everything you should write in the sentence. Okay, so this is the equation, and in this equation, this is the equation, and in this equation we have to find out this EFF. We need to find out this EFF. Okay, then take the necessary things to the left hand side and right hand side. Okay, when I do that, what I get is, this is I'm going to get. Okay, so this term is taken to the denominator, this term is taken to the denominator over here. Okay, since it is a denominator, when I take to the numerator, it will be plus EF. So this equation plus EF, I can write it as 2EF minus Cg divided by KT. Okay, so this, since it is a exponential term, take ln on both sides. When I take ln on both sides, what happens is this will be as it is, and here I am applying the ln. When I apply ln, so this order term will come to the normal, that is 3 by 2 ln of mh divided by me. Okay, then I wanted EFF, I wanted EFF, right? So that I'll take this EG to the right hand side, it will be plus EG. I'll take this KT to the right hand side. First we should take KT first to the right hand side, it will be here, and EG to the right hand side. Okay, then 2 again I'll take to the right hand side, right? When I take 2 to the right hand side, it will be 4, here it will be 2. So this whole term will become 0 because of ln is equal to 1 is equal to 0. Ultimately, what I get is the thing which we have proved. Okay. Any doubts in this derivation? Any doubts do you have in this derivation? Okay. If you don't have any derivation, then we'll move ahead to find out the another concept, another very important thing, that is finding out the conductivity of the semiconductor. We are going to find out the conductivity of a semiconductor. Okay. So conductivity means how much it is conducting. Conductivity, that is sigma. We are going to find out what is the sigma of a semiconductor. Sigma, right? This is the conductivity. Okay, if I want to apply any semiconductor to the devices, first I should know how much it is conducting or how much it is resisting. If I have copper wire or silver wire, those are highly conducting. How much it is conducting? Or if I have any semiconductor, before applying, we should know no, what is the resistance or what is the conductivity of any semiconductor. Okay, any semiconductor, that doesn't matter. So we should know what is the property of the semiconductor. Then only I can apply it to any devices. Okay, to do that, I should have the equation for that. Okay, from that equation we can easily find out what is the conductivity. Okay, let us do that. Let us consider the semiconductor like this. Let me consider the semiconductor like this. Let us say this is a semiconductor, like a wire. Let us say this is some wire. Okay, this is some wire, right? Wherein current is flowing inside this. What is current? Current is nothing but flow of electrons. So this is the flow of the charges. Flow of charge is nothing but current. So this current is flowing inside this. Okay, what is that current? Flow of electrons. Let us say the electrons are here. These electrons are flowing. Okay, so these are the electrons which flow in this direction. As electron flow in this direction, the holes will flow in the opposite direction. Okay, that means this conductivity is including both the things. Conductivity includes conductivity due to electrons plus conductivity due to holes. Okay, we have to find out the conductivity of electrons and conductivity of holes. Add both the things, I'll get the total conductivity of the semiconductor. Okay, this is the idea behind this derivation. Fine. So this electrons are moving with the velocity v. V is what? V is velocity. Okay, these electrons are moving with the velocity v. And what is the cross sectional area? A is the cross sectional area. A is the cross sectional area. Okay, now this is for intrinsic semiconductor. Since it is in intrinsic semiconductor, there will be electrons, there will be holes. We have to add and we should get this sigma. Now volume covered by the electrons. Ultimately here I want to find out what is the current flowing inside this. What is the current flowing inside that? From that current I can find out the current density, that is I divided by A is the current density. Okay, I'm just telling what all things we have to find out in this. Okay, then ultimately I have to find out what is the electron, what is the holes, conductivity for electrons, conductivity for holes, and then we have to add these two things, okay, to get the sigma. Okay, fine. First we will find out the charge flowing inside the material. What is the charge flow? Charge flow is current I. Okay, what is I? These are moving with velocity v. Okay, so the volumes swept, volume covered or swept, you can say covered. Okay, volume covered by electrons. Okay, volume covered by electrons per second is equal to, fine, it is A into V. Okay, what is A? A is the cross-sectional area. What is V? V is the velocity. Fine. Let us say these are the four electrons which are covering. These are moving in this direction. That this is taking some distance L. Okay. Earlier it was here, then it moves till here. Right? So it has covered some volume, right? It has covered some volume. This much volume it has covered. Okay. So what is that volume? Volume is nothing but length into breadth into height. Okay, length into breadth into height. Already we have this area. So this, let us say this is area into length. Again it is volume. So this is capital V, volume, right? That volume swept, this much volume is swept by these electrons. Volume swept by the electrons per second. Okay. How to write this? How to understand this area into velocity is nothing but volume. Okay, till now we understood the basic thing that volume is nothing but length into breadth into height. But why I'm writing this area into velocity? Okay, that is very simple. That is, what is this? This is volume per second. What I want volume per second, because volume into the charge if I make. Okay, that means charge per second is equal to current it will become. Okay, that's why I'm writing this as volume per second. Okay, how it is, just I'm just trying to explain you why we have taken like that. So it is length into breadth into height. Okay, per second. Okay, this is, what is this? This is volume per second. Volume per second means length into breadth into height per second. Okay, and here length into breadth I'll take it as area. Okay, then this length per second. What is length per second? Distance divided by time taken. Length per second, that is velocity. Okay, this is velocity, distance divided by time. So I can write this v divided by v into a. This is volume per second. Fine. So volume covered by electrons per second is a into v. Okay, now simple, this is only volume. It is, we have volume. Now we have to fill the charge inside this. What is the charge? Total charge is equal to total charge inside uh, the volume. Okay, inside the volume, total charge inside the volume is what? That volume into the charge we should do. Okay, so the charge inside the volume is nothing but, let us say this is n, is the number of electrons, multiplied by the charge is nothing but the charge of the electrons. Okay, so this is the number of electrons into that charge. What happens is, I'll get the charge inside the volume. Fine. The charge inside the volume is Ne into E. We will get the charge inside that, total charge inside that. So it is like, if you have 10 rupees, each student is having the charge of 10 rupees. How many number of students are there? Okay, that will become total charge of that. Right. Now this volume itself is moving this side, right? This volume is moving. So many electrons are there inside this. So many electrons are there. So many charges are there. So these charges with the volume, it is moving in this direction. That is called as the current, right? So we can write it as charge flow per second. Okay, that is nothing but charge flow per second. That is what charge flow per second is. I, that is current. Current is equal to, what I can write, it is Ne into that particular volume. When I multiply this volume per second, how much charge is there inside that? If I multiply these two things, I'll get charge flow. What is meaning of that? So this volume itself is moving this side. Okay, that means we have to multiply these two, I'll get the current inside that. Let us call this equation number 1. This is equation number 1. Now current density. So this much, I hope you understood this much. Simple it is. We should multiply these two equations. Now charge density. What is the charge density? charge density, that is equal to J. Okay, J is equal to I divided by A. What is this meaning? So I have some area like this. How much charge is flowing inside this? Okay, this is current I which is flowing. What is the cross sectional area? Cross sectional area is A. So how much current is passing through area? How much current is passing per unit area is nothing but it is the charge density, or it is called as current density. Okay, current density is equal to J. It is current density. Okay, you can say this is current density is equal to J. Fine. Now let us substitute this I. What is I? I is NEEAV divided by A. So what I got? J is equal to NEE into V. This is equation number 2. I'll write. I'm sorry. It has gone down. So here J I have taken I divided by A. Fine. Then this J is value of J is NEEAV divided by A. So A will get cancelled. Then J is equal to, this is the answer. What is current density? Current density, the current flowing per unit area is current density. I hope you understood this. Nothing more difficult things are there. It's quite easy. Then fine. Then I'll move to final equation. Okay. Only one step is remaining. Then we'll reach to the final equation. Okay, so this is the current density. Equation number 2 is the current density I have. Fine. And in this equation we have to substitute for the electron mobility. Now electron mobility, what is this new term? Okay, it is called as mu e. Electron mobility is nothing but how fast the electrons can move, how fast these will shift. It is called as electron mobility. That depends on this electron mobility depends on this velocity of the electron and the field per field, velocity per unit field, where this is electric field. This is called as electric field. Electric field. In the last class, I have already told you what is electric field. So this is electric field. So this is definition of electron mobility. Okay, then what happens is, what is the value of V? V is equal to, it is mu E into E. It will be mu E into E. And let me substitute that in the equation number 2. Equation number 2 will become, okay, N E E mu E into E. Okay, this is the term, the mobility, how fast the electrons can move inside the material. Why we are doing this all exercise? Because I want the conductivity term in the equation. That is given by, this conductivity is given by Ohm's law. Okay, this is the new Ohm's law, wherein in this case it is generalized, more generalized terms are given. Okay, this is the Ohm's law. Normally you have learned that this is V is equal to IR is the Ohm's law. Okay, this is the Ohm's law, which already we have learned, and we have solved the problems on this. In this case, what is the problem is, this resistance will change as the material changes. Length of the material, if the length of the wire is more, then resistance will be more. Okay, that will not happen in this case. Okay, this conductivity or resistivity, okay, this conductivity will be same for any length of the material. And this is current density, wherein we are considering the area also, cross sectional area, and how much current is flowing. I and area is there including in this. Okay, where E is the electric field. Okay, there are more terms including in this. This is general equation. Okay, higher equation. So at present we should understand J is equal to sigma into E. I'll not go very deep into this, and this is directly we have to take it as sigma into E. Okay, so I want this term from this equation. What is that? That too for electrons. Okay, if I can If I'm doing for electrons, subscript should be E. So it will become what? It will be J divided by E, right? Then what we should do? We have to substitute this in this equation. Let me call this equation number 3. This is equation number 4. You just number accordingly. Okay. So equation 3 will become equation 3. No, equation 4. Equation 4 will become. So this is, substitute the value of this J. What is the value of J? Value of J is Ne E mu E into E. That whole divided by E. This one get cancelled. What is the value of J? Sigma E. This is conductivity of electron we found. Okay, mu E. This is the conductivity of the electrons which we found now. Okay, conductivity of electrons we have found. Now the similarly, when I repeat the steps similarly, what I get is conductivity of hole. I'll get conductivity of hole is given as, instead of Ne, concentration of electrons, concentration of hole we should take. Charge on that particle will be same, that is E. And mobility of the electron we have taken here, we have to take mobility of the holes. Okay, add these two things, so that the sigma is equal to sigma E plus sigma H, conductivity due to electrons, conductivity due to holes. Add the things. So when I add these two things, I will remain with the E will be common, Ne mu E plus NH mu H. So this is the general equation. Okay, this is the general equation for the intrinsic semiconductor. Another thing is here. So for the uh, intrinsic semiconductor, okay, intrinsic, Ne is equal to NH, isn't it? Ne is equal to NH. Both will be same. So I'll write this as Ni for intrinsic semiconductor, and conductivity for Ni, intrinsic semiconductor. Okay, conductivity for intrinsic semiconductor, that is equal to, okay, for conductivity of intrinsic semiconductor will be, when I substitute that, so I should take this Ni outside, then E, I remain with this mobility of electron. So mobility will be different for electrons and holes. Okay, so this is the final conductivity equation, right?